Antarctica triggered hundreds of earthquakes, and the instruments built to detect nuclear detonations never noticed, not one alarm. For 10 years, the signals sat buried in raw data, invisible to the global network built to catch every serious tremor on Earth. Researchers found them after switching to local sensors clustered at 2 sites, including the Glacier, nicknamed Doomsday. The obvious explanation seemed simple: ice breaking apart into the ocean. But one cluster of quakes was recorded dozens of kilometers from where that explanation should be possible. Something is moving beneath West Antarctica that standard seismology was never built to see. Start with the number 362. That is how many of these glacial earthquakes a single seismologist found buried in 13 years of Antarctic data, published in January in the journal Geophysical Research Letters. Not 3 or 4 confirmed events, which is roughly what Antarctica had offered up before. 362 sitting in plain sight the entire time, because nobody had pointed the right kind of listening device at the right kind of signal, and because nobody had reason to think there was anything worth listening for. To put that number in context, before this study, only a small handful of Antarctic glacial earthquakes had ever been confirmed by anyone, anywhere, despite the continent holding more ice than the rest of the planet combined. Greenland, by comparison, had produced a steady, well-documented catalog of these events for 2 decades. The imbalance was never really evidence that Antarctica's ice behaved differently. It was evidence that nobody had looked at it the right way. Here is why that gap matters. Ordinary earthquakes, volcanic tremors, even underground nuclear tests all produce high-frequency seismic waves. Global monitoring networks are tuned to catch exactly that kind of signal, and they do it well, which is why a nuclear test on the other side of the planet can be confirmed within hours, sometimes minutes. Glacial earthquakes do not play by that rule. They produce almost no high-frequency energy at all, only a low, drawn-out signature that most instruments quietly filter out as noise, the seismic equivalent of a sound too low to register as a sound. So for over a decade, while global stations logged Antarctica as seismically unremarkable near these glaciers, the real activity was happening in a frequency band the world had trained itself to ignore. The researcher behind the new study did something almost embarrassingly simple. Instead of relying on the worldwide network, they went back through data recorded by seismic stations physically standing on the Antarctic ice itself, the small, remote instruments that survive brutal winters recording ground motion nobody thinks to check for years at a time. And there they were. 2 clear clusters. One at Thwaites Glacier, the glacier that earned the nickname Doomsday because a full collapse could add roughly 2 feet to global sea level on its own. The other at Pine Island Glacier, its neighbor to the east, one of the fastest changing bodies of ice on the continent. Picture what a satellite actually shows at Thwaites right now. Recent imagery captures a jagged, fractured front, choked with broken ice blocks the size of city blocks, tilting and rotating in dark water. That image is the visible half of the story. The seismic trace sitting quietly in a data archive is the other half, a jagged little line on a screen that looks, to an untrained eye, like nothing at all. Until this year, almost nobody had bothered to read it closely enough to notice what it was actually recording. The explanation that comes to mind first is the same one that explains glacial earthquakes everywhere else on the planet. Tall, narrow icebergs break away from a glacier's edge, and as they float free, they capsize, rolling over in the water. When a slab that size flips, it slams back against the parent glacier with enough force to send a real seismic wave rippling for thousands of kilometers. It is a collision, not a fracture, and it has been documented for over 20 years in Greenland, where the process is well understood and routinely tracked by a dense, continuously operating monitoring network. At Thwaites, the numbers back that story up cleanly. 2 out of every 3 of the newly found quakes cluster right along the glacier's marine edge, exactly where capsizing ice would be expected to strike. The location fits. The mechanism fits. For a moment, the mystery looks solved, and it would be easy to end the story right there. Then comes Pine Island. A meaningful share of its quakes were not recorded at the waterline at all. They were located 60 to 80 kilometers inland, deep inside the glacier's interior, nowhere near open water, nowhere near a place an iceberg could plausibly capsize. The same signal, The same kind of event on the same instruments, read by the same method. In a location the leading explanation cannot reach. That contradiction is where the real investigation starts. Before throwing out the capsizing explanation completely, it is worth testing whether it still holds up at Thwaites itself, because the timing does not look random. The newly found quakes are not spread evenly across the 13 years of data. They spike hard between 2018 and 2020, then taper off in the years after. If capsizing alone drove the pattern at a constant rate, you would expect something closer to a steady drizzle of events year after year, not a concentrated surge followed by a decline. The first candidate to explain that surge comes straight from the Greenland playbook, because it is the only well-tested model anyone has for this kind of event. Greenland's glacial earthquakes follow the calendar closely. They peak in late summer, when warm air softens the ice and destabilizes the glacier front, then fall off sharply through the winter months. It is a clean, well-documented seasonal rhythm, confirmed across 2 decades of continuous monitoring, and it has even been getting more pronounced as the region warms. Antarctica refuses to follow it. When the newly detected events are checked against the season in which they occurred, there is no clear summer spike, no obvious warm weather pattern at all. The same underlying mechanism, capsizing ice, produces a completely different rhythm on a different continent. That rules out the simplest borrowed explanation, and it forces the investigation towards something specific to West Antarctica itself, something the Greenland comparison cannot supply. The stronger candidate turns out to be speed, not temperature. Independent satellite tracking confirms that Thwaites' ice tongue, the long floating extension reaching out from the glacier's grounded body toward open water, sped up noticeably during exactly the same 2018 to 2020 window where the quake count spikes. A faster-moving tongue delivers more ice to the ocean edge more quickly, which means more opportunities for capsizing, which means more quakes. The correlation lines up almost perfectly between 2 completely independent data sets, one seismic, one satellite, gathered by different teams for different purposes. But say that sentence again slowly, because it hides the real mystery. Why did the ice tongue speed up in the first place? The honest answer, straight from the research, is that it is tied to ocean conditions, and those conditions are not yet well understood. The investigation just traded one open question for a deeper one. It is not that scientists do not know what triggered the quakes. It is that the quakes themselves are now pointing at something happening in the ocean beneath the ice that nobody has fully mapped, a process operating out of sight, underwater, under ice, under a data gap. That gap also explains something else, the very question this story opened with. Why did global instruments miss all of this for over a decade? Part of the answer is the missing high-frequency signal. But there is a second factor. Greenland's glacial earthquakes tend to be relatively large, some of them registering on a scale comparable to seismic signals from underground nuclear tests conducted by North Korea over the past 2 decades, strong enough that a worldwide network catches them without much trouble, often within the hour. Antarctica's newly found events appear to run smaller in magnitude across the board. Weaker signal, wrong frequency band, and a global monitoring system built around distant, high-powered detection rather than small local ground motion. 3 separate reasons a genuine pattern of hundreds of earthquakes went uncounted for years, hiding not because anyone hid it, but because nothing was listening the right way, in the right place, for the right kind of quiet. There is a further wrinkle worth clearing up before moving on, because a number this size invites suspicion. Most of these 362 events are still not entered into any official earthquake catalog anywhere. That is not a red flag. It is simply what happens to a signal type most databases were never designed to hold. The events are real, drawn straight from the raw instrument recordings, but the bureaucratic process of formally cataloging them, event by event, is still catching up to what the data already shows. That resolves the case for Thwaites. It does not resolve Pine Island. Go back to that inland cluster 60 to 80 kilometers from the water and run every explanation available. It is not capsizing ice because there is no open water there for an iceberg to flip in. It does not match the seasonal Greenland pattern, and it does not sit at any known point where the ice tongue accelerates the way Thwaites does. The researcher's own conclusion is blunt about it. These events remain puzzling, and they require follow-up investigation before anyone can say what is actually producing them. That is not a failure of the study. It is the study doing exactly what good evidence is supposed to do, refusing to force a tidy answer onto a signal that does not fit one. Something inland, deep in the glacier or the ground beneath it, is producing quake-like signals with no confirmed mechanism attached. It could be internal ice fracturing under stress, far from any open water. It could be a subglacial process nobody has directly observed, hidden under kilometers of ice with no instrument close enough to see it clearly. It could be something else entirely. Right now, it sits in a category familiar to anyone who follows natural mysteries closely. A real, measured data point with no accepted explanation yet, closed to speculation, but still wide open to research. So 2 glaciers, 2 clusters, 2 very different stories. Thwaites gives up its secret through a chain of solid, testable evidence. Capsizing ice, accelerating flow, an ocean process still being studied but at least identified. Pine Island gives up almost nothing, only the confirmation that something is happening there that current science cannot yet name. And it is that unresolved half of the picture that forces the investigation to widen out, away from a single glacier, and toward the broader pattern Antarctica has been showing for years. To understand what the Thwaites side of this actually means at scale, it helps to look at where glacial earthquakes were first confirmed at all, more than 20 years ago, in Greenland. That original discovery reshaped how scientists think about ice sheet behavior because it proved that a glacier's edge could generate genuine, propagating seismic waves, not just gentle creaking, but real ground motion detectable an ocean away. It was not an obvious find either. The earliest Greenland events were nearly dismissed because their slow, low-frequency shape did not resemble what anyone expected an earthquake to look like on a seismograph. It took years of cross-checking against satellite imagery of actual capsizing icebergs before researchers were confident the strange, sluggish signal was real seismic energy and not some kind of instrument artifact. Some of the largest Greenland events carry a magnitude comparable to that of an underground nuclear detonation. That is not a casual comparison. It is a real physical benchmark researchers use to describe how much energy a single capsizing iceberg can release into solid rock in a matter of seconds. Sit with that for a second, because it is the kind of number that reframes the whole story. A block of ice, falling and rolling over in freezing water, can shake the ground with force in the same range as a weapons test. And Antarctica, the emptiest, quietest seeming continent on the planet, has just been shown to be doing a version of the same thing, hundreds of times, for over a decade, without a single alarm going off anywhere in the world. Here is where the story has to slow down and draw a hard line, because similarity is not a forecast. Greenland's events are driven by seasonal warmth. Antarctica's newly found events are not. Greenland's largest quakes reach magnitudes strong enough for instant global detection. Antarctica's appear consistently smaller, which is precisely why they went undetected for so long. The shared feature is the mechanism, ice colliding with ice hard enough to shake bedrock. The different features are the trigger, the scale, and the rhythm. Borrowing Greenland's story wholesale to explain Antarctica would have been the easy move. It would also have been wrong. There is one more comparison worth testing before moving on, because Antarctica has produced a genuinely dramatic seismic event in the recent past, and it is tempting to link it to this one. Between 2020 and 2021, the Bransfield Strait, hundreds of kilometers north of Thwaites near the tip of the Antarctic Peninsula, recorded roughly 85,000 earthquakes, the strongest seismic outburst ever logged on the continent. That swarm was traced to a magma intrusion beneath a seamount long assumed to be extinct, with the strongest single quake reaching a magnitude of 6 and ground displacement measured in centimeters detected on a nearby island. It is a genuinely staggering figure, 85,000 earthquakes at one site in under a year. And it is easy to see why someone might fold it into the same headline as the new glacial quake discovery. One big story about Antarctica suddenly becoming seismically restless everywhere at once. But check the mechanism, and the two events fall apart from each other immediately. The Bransfield swarm came from magma forcing its way through rock along an active tectonic boundary, a volcanic and geological process building for tens of thousands of years. The Thwaites and Pine Island signals come from ice physically striking ice at a glacier's edge, hundreds of kilometers away on a completely different piece of the crust. Different trigger, different location, different physical process governing what happened, connected only by the calendar, not by cause. That correction matters more than it might seem. It would have been the simplest story to tell, that Antarctica is somehow waking up all at once, one continent, one growing threat. It is also the wrong one. What is actually happening is two unrelated processes, one geological and largely explained by existing science, the other glaciological and only now coming into focus, both surfacing in the same short stretch of years purely by coincidence of timing, not by shared cause. What that leaves behind is a narrower, more precise picture. Thwaites is producing a well-explained seismic signature of accelerating ice loss, tied to warming ocean water whose exact behavior beneath the glacier is still being mapped in detail. Pine Island is producing an unexplained signature from a location the leading theory cannot reach. Both sit on the same glacier system that scientists already treat as the single largest wildcard in near-term sea level projections, the one piece of ice whose behavior could shift the global timeline faster than any other. And that is the variable now controlling how seriously this new evidence should be taken. Return to the present, because none of this is purely historical. British Antarctic Survey glaciologist Robert Larter has said the last floating shelf bracing the eastern side of Thwaites, the structure that has been slowing the glacier's slide into the ocean like a cork wedged into the mouth of a bottle, is very likely to break apart sometime this year. What is confirmed? Satellites already track visible fracturing spreading across that shelf, season after season. What is interpreted? The newly cataloged quakes likely reflect the same accelerating discharge putting stress on that shelf today, two different instruments telling a version of the same story. What remains speculation? Whether Pine Island's unexplained cluster signals a similar hidden process building somewhere else along the coast, one nobody has confirmed yet. None of this means sudden catastrophe. A full Thwaites collapse, should it ever happen, unfolds over centuries, not headlines, and would add roughly 2 feet to global sea level over that time, with the wider ice sheet behind it holding back several times more. What is close is narrower and still significant. The loss of one structural brace this year, accelerating a process that has already been underway for decades. What researchers are watching now is specific. Continued cataloging of events at Pine Island to finally identify their source, satellite tracking of ice tongue speed at Thwaites, and the ocean temperature data that first tied into that 2018 acceleration. None of the instruments out there are equipped to settle the Pine Island question by themselves. What changes the picture is patience, another season of recordings, another pass of satellite imagery over ice nobody can walk on to check by hand. For now, the honest answer sits exactly where the evidence leaves it. One glacier's earthquakes explained, one glacier's earthquake still unexplained, and a floating brace on the coast between them that is not waiting for either answer to finish breaking. Somewhere on the ice right now, a seismic station is quietly logging a waveform nobody has decoded yet, while a few hundred kilometers away, the last brace holding back one of the largest glaciers on Earth keeps cracking, season after season, in real time.